Hello, this lesson is about displacement and density. It is real world applications for volume. So, how do you find the volume of an irregular object or shape? Sorry about that. Silly of me. So, we've talked about uniform shapes, prisms, and even composite shapes that are made of different things, of different shapes that we can find the volume, we know its formula, we can add them together or even subtract them. But what about something like this? You can see it has lots of divots, right? Crevices, indentations, pointy parts. I mean, you could guess and approximate a prism and a pyramid, but it wouldn't be very close. It wouldn't be exact. So, is there a method that we could do to find the volume for this, be really accurate, and also not destroy the object, right? So there is something called displacement, and in particularly fluid displacement, meaning liquid. So when you talk about fluid displacement and the volume of the liquid that is being displaced or moved by that object, that's the displacement. And the volume of that liquid that is moved or displaced is equal to the volume of the object. So this is called a graduated cylinder, something you may see in a science class. And we can see that the water is right here, right? Here's the level. So it looks like 150 milliliters. 150 milliliters, which goes with cubic centimeters. And when you drop it in, the water rises. This is the displacement. Right? So the rock displaced that much water. So what's the volume? Well, let's see. Okay, my eyes having a hard time reading that. Okay, let's see. Okay, get a pen. So that's 2, 4, 6. So it looks like it went up to 100. So it was 150 and then it goes 156. So the displacement is 6 milliliters, which corresponds to 6 cubic centimeters, right? So that's the volume of our rock. Pretty cool, right? Displacement. All right, so let's do a problem. Take a moment to pause and read it and draw a picture to help you out. So Captain Jack wants to find the volume of a gold ground he found. He finds a rectangular chest that measures 45 by 65 by 40 centimeters and fills it with water. He gently puts the crown in the chest and the water rises a centimeter. What is the volume of the crown? Now, when you have dimensions, and even when I'm baking, there's measurements on my pans. So when you have the 3, it's length, width, and height, or depth. So this last dimension is always the height or the depth of the box or the pan or even a bookshelf. Because length and width are hard to determine which one's which, the shorter one or the longer one, but it's the ones on the bottom. So I'm going to draw a quick sketch of this. Okay, so 65 and then 40. Okay, so here's our chest. So 45, 65, and again, that last number that's always at the end, that's going to be the height or depth of it. Oh, I should have used black, because now for water, I'm going to use a different color. Now you're going to say, hey, Miss Mendoza, and when I say this, the water, the crown is completely submerged. So it has to be completely underwater. So the water, and you're like, but it didn't tell me how much it started with. It doesn't matter. Because this is slightly different than the rock one earlier. Because once you put in the crown, okay, yeah, that's my crown. Really ugly crown. Once you put in the crown, whatever it started with, the water is going to rise to a different level. And that's all you really care. You just care about that one little sliver of water, that rectangular prism of water. So I don't need, for this one, because it just tells me how much it rose, I didn't need to know how much it started with or how much it ended with, because no matter what, if I was given that and subtracted it, it would still be just 1 centimeter. So it's just the change, right, of water. So really, the rectangle that we're looking at of water is this, right? So it's 1 by 45 by 65. So I'm going to find the volume of the water. And it's 45, oopsie, can't type. 45 times 65 times 1. And it's 29, or you didn't need to multiply the 1. Centimeters cubed. Right? Okay. Now, another cool thing about volume, and this is something, and displacement is something that mathematicians have known for years. And when I'm talking about years, before Christ years. So this idea of displacement, because they didn't have all the technical things that we have now. Now, another application is density. All matter has a certain type of density, and density is measured by the mass of matter. We are all made of different kinds of matter per unit volume, which means per unit just means this is divided by volume. So here's the formula. Density equals mass divided by volume. I'm going to just take a quick moment to explain mass, which I'm not very good at, but mass and weight are different. Mass is how much matter is something in an object. Weight is about gravitational pull. Now, they're both measured in weight, like pounds they're both measured in ounces or grams or pounds. So they seem identical, even though there's slight difference. So when you see it, we're going to be talking about weight for us, but they are different ideas. All right. So let's talk about density and what that is. So I have these 4 cylinders, and they all have the same volume. As we can see that, the heights are all the same. Right? And the diameters are all the same. But we can tell these are different materials. Now, it's not in any order. I just wrote them down because the picture that I've taken from the internet didn't say which one was which. Do you know which one is which just looking at it? Maybe one of them. Copper, right? Copper is the metallic orangey one. But the other ones, I'm not so sure. But if you pick them up, would they all feel the same? Now, if you know anything about the difference between aluminum, which hopefully you have some in your kitchen, aluminum foil, as opposed to steel, they'd be very different. So if you picked up each of these cylinders, their weights wouldn't be the same. Have you ever picked something up and you're like a fork or a bowl, and you're like, wow, that has a lot of weight to it. And you're like, wow, that's heavier than I thought it was. Or vice versa. You pick something up. Often I think of statues or garden things. I pick it up and I'm like, oh, it's really light. I thought it would be heavier. And that has to do with its density. So you can have many things with the same volume, but when you pick them up, their density is different because the matter it is made up is not the same. Some are more dense than the others. So let's look about the other way. What if things had equal mass? So that means their weights are the same. Now we can see if their density, and density is consistent. Your density never changes. So, and this is why they said mass of the matter per unit. So you take whatever the weight is divided by the volume, and you'll get this number. This number is constant for whatever material. So copper, no matter what the weight or volume, it will always have the same density for all copper items. So if we're looking at this, we can see that this material, if all the mass is the same, so their weights are the same, if you pick them up, they're going to be the same weight. But it takes way more of this to equal to this, which is less. So here are the different metals. Do you know which one goes to which? Could you guess which one is which? So copper, we can probably guess is this one over here. But could you guess this one? Yeah, I'm going to guess that's aluminum too. And I'm going to guess this may be steel, or I mean lead, because lead's pretty heavy. How do I know? Chart. So because we can figure out and measure different quantities and sizes of material, their mass and their volume, people have come up, scientists, mathematicians, have come up with their densities. So this can help you figure out which material is which. So here's the 5 densities of these metals. So you can look, and it's listed in alphabetical order. We can see that aluminum clearly has the smallest density, so it's really light. It's not thick or dense. And density, I often think of cake or brownies, and when a brownie is really dense, right, we think of it really heavy and gooey and really good. But cake, even though maybe have the same volume and height, often has a lot of air bubbles. So then it's very light and airy. So its density is much lighter. All right, the heaviest one is lead, right? So, okay, this is probably aluminum. I think that's Al. This is lead, periodic table. No, I can't remember that. We know this is probably copper. Okay, so, and now we're going to look at zinc and tin. Well, if I'm looking over here, it looks like there's more of this one, right? So this probably has a smaller density than this one. So let's look. So tin and zinc, they are pretty close. Tin is 5.75, and you can see the units. The mass's weight is measured in grams over the volume, centimeters cubed. So that tin is lighter, and then zinc, tin is less dense, and zinc is more dense. I can't use the weight. So we're looking over here. I'm going to say this is tin, and then this is zinc. Okay. Now, there's lots of charts and tables for your homework tonight. The book online, It's on page 558, and you're going to need it for some of your homework problems. So just wanted to show you. So you don't need to copy this. Don't copy this. Just wanted to reference this to show you where it is. Or to do your homework, you can always just use this video and keep the slide open to help you. All right, so let's go back to that crown. So after wearing the crown for a while, Jack suspects the crown is not made out of gold. You know, he's a pirate. He knows about gold. So he decides to weigh the crown. Using a scale, he determines the crown is about 33,000 grams. Is the crown made out of gold? Show evidence that supports your answer. Now, when we talk about density, remember I said all the material, so all aluminum has the same density. So no matter how much, you can always figure that out. So gold will always have the same density. This is how people often tell the purity of something. Gold, there's some other equipment that they have now too that can determine that. But again, you don't want to destroy the piece either, because if it's real, then you've messed it up. So this is one way to do it. All right, so we know that density is mass over volume. Okay, so we know that the mass is 33,000 grams. Okay, and what was the volume? Oh, well, we found the volume. I forgot to write it down someplace. Okay, oops. Sorry. Patience. Oops. Okay, so let me write that down. I have 2925 centimeters cubed. Okay. Okay. So 2925 centimeters cubed. Okay, and then you're just going to divide it, because the chart that we had, 1, 2, 3, had a table. 2925. Okay, so this is approximately 11.2821 grams per centimeter cubed. So is that gold? All right, so let's look at the table that we have. Go back. 11.28. Okay, oopsies, not that way. Okay, gold is 19.3. So that's not even close. So maybe if it was close, maybe 19 flat, or maybe 19.5 or 19.88, because maybe Jack's equipment is not the most accurate, his scale. But I don't think that's close. Oh, look at the one underneath. So we had 11.2821. That's pretty close to lead. So I'm going to say it's probably lead. Or maybe, no, I'm going to say it's probably lead. Right? So this shows me no. Not gold. And remember, support your answer. So show evidence. So here's my evidence, not gold. The density of gold is 19, what did we say? 19.3. Grams per centimeter cubed. So they're not equal. All right, so that is evidence. This is your evidence. This is your work. This is your conclusion. So you can, so I know that you've analyzed it and you can come up with a conclusion. All right. Thanks so much for watching. Hope you enjoyed this one. It was a lot of fun. Bye.